Right now, while you're listening to these words, something is happening that almost nobody on Earth is thinking about. A curtain of molten rock is shooting hundreds of feet into the air, not once, not as a single explosion, but over and over again. The glowing fountains rise, collapse, and rise again, painting the night with rivers of orange light that can be seen from miles away. And nobody expected this volcano to be behaving quite like this. It is not the tallest volcano on Earth. It is not the most explosive. It is not even the largest volcano in Hawaii, yet it is one of the most closely watched pieces of land anywhere on the planet, because what happens here helps scientists understand how our world is still being built. One of these lava fountains has recently reached nearly 300 feet, about 90 meters. That is roughly the height of a 30-story building. Imagine molten rock climbing higher than an apartment tower before falling back to the ground as glowing fragments. That is happening today. The researchers observing these eruptions are not describing them as simply interesting. Their reports focus on changing eruption patterns, rapidly evolving vents, and behavior that still cannot be predicted with complete confidence. Stick around because I'm about to walk you through what scientists have actually confirmed about Kilauea's latest eruption. And hit subscribe now, because this channel breaks down real scientific discoveries without the exaggeration. Let's go back to where this story actually begins. Long before satellites watched Hawaii from space, long before drones hovered over lava lakes, long before live-stream cameras showed eruptions to millions of people, there was a young geologist trying to understand why one volcano refused to behave like the others. In 1912, a 30-year-old geologist named Thomas Augustus Jagger Jr. helped establish what would become the Hawaiian Volcano Observatory. His office overlooked one of the most active volcanic landscapes on Earth. His daily work was surprisingly ordinary. He measured earthquakes, recorded temperatures, sketched cracks in the ground, compared handwritten notes, day after day, week after week. Most people thought volcanoes were disasters that occasionally erupted. Jagger believed something different. He believed volcanoes were living geological systems. If scientists watched them continuously, instead of only after disasters, they might begin to understand how eruptions actually worked. At the time, that idea was remarkably ambitious. Permanent volcano observatories barely existed. Continuous monitoring was still unusual. Many eruptions happened without detailed scientific observations. Jagger wanted to change that. His timing could not have been better. Kilauea had already been active for centuries before anyone arrived with notebooks and instruments. Native Hawaiian traditions had described its behavior for generations, connecting the volcano with Pele, the revered deity associated with volcanoes and fire. Those traditions preserved careful observations of changing lava lakes, explosive episodes, and shifting landscapes long before modern geology developed its own explanations. Modern science added instruments. It did not replace centuries of observation. Jagger understood that every eruption left behind information. The challenge was collecting enough of it. Every earthquake, every crack, every inch of ground movement, every gas sample, every change inside the crater. Individually, none of these measurements explained much. Together, they began revealing patterns. Slowly, painfully slowly, sometimes over decades. That patient approach transformed volcanology. Instead of asking why an eruption happened after the fact, scientists started asking whether the volcano had shown warning signs beforehand. Over the following century, better instruments arrived. Mechanical seismographs became digital networks. Occasional field surveys became satellites capable of measuring tiny movements of Earth's surface. Gas measurements became continuous monitoring stations. Thermal cameras watched heat escaping from vents day and night. Today, scientists from the U.S. Geological Survey's Hawaiian Volcano Observatory combine these observations with satellite data and airborne measurements to understand Kilauea almost continuously. Yet despite more than a century of monitoring, one fact remains remarkably humbling. Researchers still cannot predict the exact moment when a new eruptive pulse will begin. They can identify increasing probabilities. They can recognize warning signals. They can monitor magma moving underground. But the precise timing of individual lava fountains remains close to impossible. That uncertainty is one reason Kilauea continues attracting scientific attention. It is among the best monitored volcanoes on Earth. If prediction remains difficult here, it becomes even harder almost everywhere else. Then came another turning point. In 2018, Kilauea experienced one of the most significant eruptions in its recorded history. The summit collapsed dramatically. Entire neighborhoods were destroyed farther down the East Rift Zone. New coastline formed where lava entered the Pacific Ocean. Thousands of earthquakes accompanied the changing plumbing system beneath the volcano. The eruption fundamentally reshaped the summit caldera. Scientists suddenly found themselves studying an entirely new volcanic landscape. Years passed. The volcano quieted. Then activity gradually returned, beginning in 2020 and continuing through 2021, 2023, 2024, and into 2025. Kilauea entered a series of renewed summit eruptions. Rather than one uninterrupted eruption, scientists observed multiple eruptive episodes. Some lasted days, others ended, then restarted. Each episode provided another opportunity to study how magma rises from deep underground before reaching the surface. Each episode also raised new questions. Why do some eruptive pulses stop almost as suddenly as they begin? Why do lava fountains sometimes grow dramatically taller before weakening again? Why do some vents remain active while nearby fractures fall silent? After more than a century of measurements, researchers still cannot fully explain every answer. And that is exactly what makes Kilauea extraordinary. Not because everything about it is known, but because every eruption teaches scientists something they did not know before. Among those recent eruptions, one image captured global attention: a towering lava fountain approaching 300 feet. Again, about the height of a 30-story building, one of the signature numbers we'll return to throughout this story, because that single number tells us something remarkable about the enormous energy moving beneath your feet. To understand why lava can suddenly shoot hundreds of feet into the air, you first need to understand what magma is actually doing below the surface. The story begins deep beneath Hawaii, not inside the volcano itself. Far below it, scientists explain Hawaii's volcanism through what is known as a mantle hotspot. In simple language, a long-lived source of unusually hot material rises from deep within Earth's mantle. As the Pacific Plate slowly moves across this hotspot over millions of years, new volcanoes form one after another. Think of holding a sheet of paper over the flame of a candle. The flame stays nearly in one place. The paper moves. Burn marks appear in a line. That is similar to how the Hawaiian island chain formed. Not because the hotspot traveled rapidly, but because the tectonic plate above it kept moving. Deep underground, rock becomes hot enough to melt partially. That molten material is less dense than the surrounding solid rock. Because it is lighter, it slowly rises. Those rising melts collect into underground reservoirs. But they do not simply remain there. They continue building pressure. Tiny dissolved gases remain trapped inside the magma: water vapor, carbon dioxide, sulfur dioxide. As long as pressure stays high, much of that gas remains dissolved, similar to carbon dioxide staying mixed inside a sealed bottle of soda. But once the magma begins moving upward, everything starts to change. As magma rises, the pressure around it drops. That changes everything. The dissolved gases no longer remain comfortably mixed within the molten rock. Tiny bubbles begin forming. At first, they are microscopic. Then they grow. Then they merge. The higher the magma rises, the larger those bubbles become. Think about opening a bottle of sparkling water. While the bottle is sealed, the carbon dioxide remains dissolved. Twist the cap. Pressure disappears. Bubbles race upward almost instantly. Inside a volcano, the same physical principle operates. Only instead of harmless bubbles inside a drink, the bubbles are expanding inside molten rock that may already be hotter than 1,100 degrees Celsius. That is hot enough to melt many common metals. Hot enough to keep rock flowing, almost like thick syrup. Hot enough that every glowing fragment you see has only recently been part of Earth's interior. Those expanding gases push against the surrounding magma. If enough gas accumulates beneath a narrow opening, pressure increases. Eventually, the magma can no longer contain it. The expanding gases launch molten rock upward, not because someone or something exploded in the everyday sense, but because compressed volcanic gases suddenly found a path to escape. Those gases do not simply disappear. They continue expanding. They continue accelerating the lava upward. They continue feeding the fountain until the underground pressure begins falling again. That is why lava fountains often grow gradually, reach a peak, then slowly shrink. The underground plumbing system is constantly adjusting. Pressure rises, pressure falls. New magma enters. Gas escapes. Channels widen. Other channels seal themselves shut. Everything beneath the surface remains in motion. That is one reason volcanologists often describe volcanoes as dynamic systems rather than fixed structures. The mountain you see is only the visible part. Most of the action happens where nobody can watch directly. Instead, scientists must infer what is happening from indirect evidence. Earthquakes, ground deformation, gas chemistry, satellite observations, thermal imagery. Every measurement becomes another clue. No single instrument tells the whole story. Together, they begin revealing what the volcano is doing. But even with all those tools, researchers still cannot directly observe the entire plumbing system beneath Kilauea. It remains one of volcanology's greatest challenges. People often assume Kilauea is easy to study because scientists can visit it. Compared with distant planets, that is true. Compared with almost every other scientific problem, it is not. The magma feeding today's eruption lies kilometers beneath the surface. No camera reaches it. No human has ever seen those underground pathways directly. No drill has penetrated the entire active magma system. Scientists are trying to reconstruct an invisible structure using indirect measurements. Imagine standing outside a house. You cannot enter. You cannot look through the windows. You cannot remove the roof. But someone inside keeps turning lights on and off. You hear footsteps. Doors open. Water starts running. From those sounds alone, you must figure out where every room is. That is remarkably similar to modern volcanology. Every earthquake acts like one footstep. Every gas measurement becomes another clue. Every centimeter of ground movement suggests magma has shifted somewhere below. One instrument alone means almost nothing. Hundreds together begin revealing a pattern. The Hawaiian Volcano Observatory operates one of the densest volcano monitoring networks anywhere on Earth. Seismometers record earthquakes too small for people to feel. GPS stations measure ground movement with extraordinary precision. Satellite radar can detect changes in elevation measuring only a few centimeters. Think about that. Scientists can sometimes measure the ground rising by less than the thickness of your little finger, across an entire volcanic summit. From space, those tiny changes matter, because magma occupies space. When underground reservoirs fill, the ground often rises slightly. When magma drains away, the surface may slowly sink again. It is like watching bread rise in an oven. The dough expands because something inside it is changing. The crust above the magma responds in much the same way. Not instantly, not dramatically, usually only a few centimeters, but enough for modern instruments to detect. Gas measurements provide another piece of the puzzle. Sulfur dioxide is especially important. Fresh magma contains dissolved sulfur. When that magma approaches the surface, sulfur dioxide escapes into the atmosphere. Increasing sulfur emissions often indicate new magma has arrived at shallow depths, but not always. Sometimes gas escapes without producing an eruption. Sometimes eruptions begin with only modest gas increases. Sometimes earthquakes increase. Sometimes they do not. Nature rarely follows perfect rules. That uncertainty remains frustrating. It also makes every eruption scientifically valuable, because each one tests existing models against reality. And reality does not always cooperate. When summit eruptions resumed after the major 2018 collapse, scientists expected activity. They did not necessarily expect the repeated pattern that followed. Instead of one continuous eruption, Kilauea began producing multiple eruptive episodes. An eruption would strengthen, then weaken, sometimes stop completely. Days later, another episode would begin. The cycle repeated again and again. During several episodes observed between 2024 and 2025, lava fountains climbed toward 300 feet. That number deserves another pause. 300 feet. About 90 meters. Roughly the height of a 30-story building. Imagine molten rock reaching the roof of a downtown skyscraper, then falling back into the crater as glowing fragments. That image seems extraordinary. Yet for Kilauea, it is entirely possible under the right conditions. Scientists believe these tall fountains reflect changing gas pressure within shallow magma reservoirs. More gas, more expansion, higher fountains, less gas, lower fountains. Simple in principle, much harder in practice, because researchers still cannot predict exactly how much pressure has accumulated before each eruptive pulse. That remains one of the unanswered questions. Why does one episode produce modest lava flows, while another launches fountains approaching 300 feet? The answer almost certainly involves gas content, magma supply, underground geometry, and pressure. Exactly how those factors combine remains an active area of research. Again, one volcano, 100 years of observations, and researchers still cannot fully explain every episode. Science often advances that way, not by removing every mystery, but by reducing uncertainty one eruption at a time. Long before anyone sees glowing lava, the volcano often begins moving, not dramatically, quietly. The summit may slowly rise, only a few centimeters, perhaps less, enough that nobody walking nearby would notice, but enough for GPS instruments to detect immediately. Imagine placing a basketball underneath a thick blanket. As the ball inflates, the blanket lifts slightly. That is similar to what happens above a filling magma reservoir. Fresh magma enters underground storage. Pressure increases. The ground bulges upward. Eventually, something has to give. Sometimes pressure escapes harmlessly. Sometimes it migrates sideways. Sometimes it reaches the surface. That gradual inflation has become one of the most valuable forecasting tools available to volcanologists. Yet even here, the story refuses to stay simple. Some periods of inflation never produce an eruption. Some eruptions begin after only modest inflation. Others follow rapid deformation. Scientists can measure the movement. Understanding exactly what it means remains considerably harder, which brings us to another important lesson from Kilauea. The volcano is not behaving randomly, but neither is it behaving like a perfectly predictable machine. It is a natural system, with countless interacting variables. And despite more than a century of observation, researchers are still learning its language. Before lava reaches the surface, the volcano usually speaks, not with sound, with earthquakes. Most of them are so small that nobody standing nearby notices them. A person may walk across the summit without feeling a single vibration, yet sensitive instruments record hundreds of tiny events over days or weeks. Each earthquake represents rock breaking, or slipping, or adjusting to magma forcing its way through narrow fractures. Imagine trying to push thick honey through a bundle of drinking straws. Some straws remain open, others clog. Pressure builds. Eventually, one path gives way. Inside Kilauea, something similar happens. The magma does not travel through one perfectly smooth pipe. Instead, it moves through a complicated network of cracks, chambers, and conduits that have formed over thousands of years. Some pathways widen, others collapse. Some remain active for decades, others become sealed. Every adjustment creates stress. Every release of stress can generate an earthquake. This is why seismometers are among the first instruments scientists watch when activity begins changing. One earthquake tells very little. A sequence tells a story. If earthquakes begin migrating upward, magma may also be moving upward. If they shift sideways, magma could be entering another section of the volcano. If they suddenly stop, the interpretation becomes more difficult. Did magma stop moving? Did it find an open pathway requiring less rock to break? Or did pressure simply redistribute somewhere else? Researchers cannot always answer immediately. That uncertainty is important. Science is strongest when it clearly separates observations from interpretations. The observations are straightforward. Earthquakes occurred, ground moved, gas emissions changed, lava erupted. Exactly how every underground process connects remains an area of active research. Kilauea continues reminding scientists that nature rarely follows a perfectly simple script. If lava is the volcano's visible face, gas is its invisible heartbeat. One of the most important gases released during eruption is sulfur dioxide. It is colorless. You cannot usually see it directly, but modern instruments can measure it with remarkable precision. Ground stations continuously sample the air. Aircraft sometimes fly through volcanic plumes. Satellites orbiting hundreds of kilometers above Earth can also detect sulfur dioxide spreading through the atmosphere. Think about that for a moment. Scientists can identify a cloud of volcanic gas from space, not because the gas glows, but because it changes the way sunlight passes through the atmosphere. Those measurements reveal something happening underground. Fresh magma contains dissolved gases. As pressure decreases during ascent, those gases escape. Higher sulfur dioxide emissions often indicate that new magma has reached shallow depths, but often is not the same as always. Sometimes, sulfur emissions increase without producing major lava fountains. Sometimes, lava appears after relatively modest gas changes. Sometimes, multiple processes happen simultaneously. Again, the volcano refuses to follow simple rules. Researchers combine gas measurements with earthquake data, then with GPS observations, then with satellite radar. Each method has strengths. Each also has limitations. Only together do they provide a clearer picture. Even then, parts of that picture remain missing. Scientists still cannot directly observe the deep magma pathways feeding every eruption. Those structures remain hidden beneath kilometers of solid rock. Let's return to one of our signature numbers. 300 feet, roughly 90 meters, about the height of a 30-story building. It is an impressive image, but scientifically, why does it matter? Because fountain height tells researchers something about energy. A lava fountain is not simply molten rock being thrown upward. It is evidence of expanding volcanic gases, transferring enormous energy into moving magma. Higher fountains generally indicate stronger gas-driven acceleration. Lower fountains suggest less pressure available to propel the lava. That relationship seems straightforward. Reality is more complicated. The shape of the vent matters. The viscosity of the magma matters. The amount of dissolved gas matters. The speed at which new magma arrives matters. Even subtle changes in underground geometry may influence the height of a fountain. Imagine placing your thumb over the end of a garden hose. The water suddenly shoots farther. Remove your thumb. The stream shortens. The water supply has not necessarily changed. The opening has. Volcanic vents can behave similarly. A relatively small change underground may produce a noticeably different fountain above ground. This is one reason volcanologists avoid relying on a single measurement. A spectacular fountain may attract headlines. Scientists are equally interested in everything surrounding it: the earthquakes beforehand, the ground deformation, the gas chemistry, the lava composition, the cooling rate. Every observation helps explain why this particular episode behaved differently from the last. Even after decades of monitoring, researchers still cannot fully explain why certain eruptive episodes transition into especially tall lava fountains, while others remain comparatively gentle. The answers likely involve several interacting processes rather than one simple cause. That complexity is not a weakness of science. It is an accurate description of nature. Most natural disasters destroy landscapes. Kilauea does something more unusual. It destroys and creates. When lava reaches the ocean, it cools rapidly. Layer after layer of solid rock accumulates. Over time, entire sections of new coastline can appear. Imagine pouring thick concrete into the sea. Once it hardens, the shoreline extends outward. Volcanic lava behaves in much the same way, although the process is vastly hotter and considerably more dangerous. During the 2018 eruption, enormous volumes of lava entered the Pacific Ocean. The island literally became larger. New black rock replaced open water. Maps had to be updated. Satellite images showed coastlines changing within weeks. That transformation is one reason Hawaii remains one of Earth's youngest island chains. These islands are still under construction. Every eruption contributes another chapter. Every lava flow modifies the landscape. Every cooling surface becomes tomorrow's rock. Eventually, rain falls. Wind erodes the lava. Tiny organisms begin colonizing fresh ground. Plants arrive. So do insects. Years later, entire ecosystems may develop where glowing lava once flowed. It is one of geology's most remarkable cycles. Destruction giving way to creation. Not immediately, not dramatically, but inevitably. And beneath that new landscape, the hotspot continues supplying heat. The Pacific Plate continues moving. The process continues. Exactly as it has for millions of years. One of the easiest mistakes to make when watching a volcanic eruption is assuming that every episode is a beginning or an ending. In reality, most eruptions are neither. They are moments within a process that has been unfolding for hundreds of thousands of years. Kilauea itself is estimated to be between 200,000 and 300,000 years old, although only part of that history has taken place above sea level. The volcano has erupted repeatedly throughout recorded history. It has also experienced long, quiet periods. Neither state lasts forever. The eruptive episodes observed during 2024 and 2025 are part of that longer story. Scientists at the U.S. Geological Survey's Hawaiian Volcano Observatory continue monitoring earthquakes, ground deformation, gas emissions, and lava activity around the clock. Every new episode adds another data point. Every pause tests existing models. Every renewed eruption improves scientists' understanding of how this volcano works. But there are limits to what monitoring can achieve. Researchers can often recognize that the probability of eruption is increasing. They can identify magma moving beneath the summit. They can measure inflation. They can detect changing sulfur dioxide emissions. What they still cannot do with complete confidence is answer one simple question. Exactly when will the next eruptive pulse begin? That remains close to impossible. Nature simply contains too many interacting variables. Pressure changes, gas content, underground geometry, rock strength, magma supply. Each influences the others. No instrument measures all of them directly. That uncertainty is why volcanology remains an active scientific field, rather than a solved problem. Future eruptions will almost certainly answer some questions. They will probably create new ones at the same time. At first glance, Kilauea might seem like a local story, a volcano on an island in the Pacific. Beautiful, powerful, but far away. In reality, its importance reaches much farther. Kilauea is one of the world's best natural laboratories. Because scientists can monitor it so closely, the lessons learned here improve volcanic hazard research everywhere. Methods developed in Hawaii are used to interpret activity at volcanoes across the world. The instruments, the monitoring strategies, the computer models, the warning systems, many have been refined through decades of observations here. Understanding Kilauea also helps researchers understand Earth itself. Volcanoes recycle material from deep within the planet. They release gases into the atmosphere. They build new crust. They reshape landscapes. They reveal processes hidden beneath our feet. In a sense, every eruption provides a glimpse inside Earth, without drilling thousands of kilometers into the mantle. That is extraordinarily valuable, because humanity has never directly reached Earth's mantle. The deepest scientific drilling projects extend only a tiny fraction of the distance to the planet's center. Almost everything we know about Earth's interior comes indirectly, from earthquakes, from laboratory experiments, from computer models, and from volcanoes, like Kilauea. One of the most remarkable aspects of this eruption is not how much scientists know, it is how clearly they describe what they do not know. Researchers understand the broad physics of lava fountains. They understand gas expansion. They understand magma ascent. They understand hotspot volcanism. Yet important questions remain. Why do some eruptive episodes end suddenly? Why do neighboring vents behave differently? How exactly does the underground plumbing reorganize itself after each eruption? Researchers continue investigating these questions. Some answers may emerge in the coming years. Others may require decades of additional observations. That is how science progresses, not by pretending uncertainty does not exist, but by measuring it, reducing it, testing every explanation against new evidence. Kilauea reminds us that even one of Earth's most studied volcanoes still has secrets. That should not reduce our confidence in science. It should increase our appreciation for how complicated the natural world truly is. So what does all of this actually add up to? A volcano, a 300-foot lava fountain, a 30-story column of molten rock, more than 100 years of continuous scientific observation. Those numbers are impressive, but together, they tell a deeper story. They remind us that Earth is not a finished planet. It is still changing, still moving, still creating new land beneath our feet. The glowing fountains eventually fall, the lava cools, the ground hardens. But deep below the surface, the process continues, silently, patiently, long after the headlines disappear. And perhaps that is the most extraordinary part. Not that Kilauea erupted again, but that, after more than a century of careful observation, it can still surprise the people who know it best. If one of Earth's most closely monitored volcanoes can still reveal something unexpected, it is genuinely worth wondering what other volcanoes, and other parts of our planet, might still be hiding. If you enjoyed this documentary, consider subscribing and turning on notifications. Here, we focus on discoveries grounded in real published research, rather than exaggerated headlines. Because the real story is almost always more fascinating than the hype.